How do you do, ladies and gentlemen, and boys and girls, and teachers and people? I'm Julius Sumner Miller, and physics is my business. And our special business today, and for several days to come, will be on the subject of waves and sound. And this first program, this first lesson, more deliberately on kinds of waves and their fundamental properties. Now, by way of preamble, if I were to put the question, what is a wave? You would find it very difficult to answer, because some simple questions are very difficult to answer, like what is a tree or what is a hole, which a child once answered this way: a hole is to dig, which I think is terrific. So we best tell what a wave is by showing different kinds of waves. And this view we call in physics the operational. I can't very well tell you what a wave is without writing some formidable mathematics, which may indeed only obscure the matter. But if I show you some different kinds of waves, you will get a feeling for what a wave is. Now, we characterize waves generally into transverse waves and longitudinal, also called compressional, for a reason you will see. Now let me show you a transverse wave. I have laid out in front of us here a rubber tube. I'm going to take this one first. There are two, in fact. Here is a rubber tube which is so long, under such tension, and so fat. We speak of the linear density. Remember, the strings on a piano, some are long and skinny and some are short and fat. So this string is fixed at that end, it's fixed at this end, it has a certain tension, a certain linear density. I'm going to give rise to a pulse in it by depressing a part of that tube. And watch. Something went down and something came back. The wave propagation delivered only energy. Nothing of this tube went anywhere except up and down, as I shall show you a little later. So the velocity of this transverse wave, where the particle disturbance is this way and the energy propagation this way, had a certain velocity. Now I'm going to increase the tension, and I'm going to create a pulse again. Watch it. Oh, much faster, much faster. Now I'm trying to get in a place where we can see it better with respect to the table. Now I've increased the tension, pulling it very tightly. Oh, very fast, very fast. Now even tighter still, very tight. Oh, enormously fast. Now that tube is, as I often say, empty, but it isn't. It's filled with air. Now I have another beside it, which is filled with sand. This one is filled with sand. So its linear density is vastly greater. Now, if I had all of the properties the same as in the first one, and I give rise to a pulse, it moves with less velocity, but higher tension, higher velocity. So I have demonstrated a transverse wave, and I will write for you the velocity with which a transverse wave moves. It is given by the square root of the tension divided by the linear density. That is how fat it is. Now, that is a transverse wave. Indeed, all waves answer this certain property. Their velocity is governed by an elastic property divided by an inertia property. And this will become clearer with further demonstrations. So this was a transverse wave. Now, the next kind, longitudinal, also called compressional. Compressional. Let me show you why it is compressional. Remember, in the case of the transverse, the particle disturbance was up and down, and the energy propagation at right angles to it. Now I have a spring, often called commercially a slinky. It is so fat, wound so tightly, under certain tension, I'm going to give rise to a pulse by squeezing some up, storing some energy, and letting it go. Watch now. A compressional pulse went down. I'll make it more deliberate. Oh, not only did a compressional pulse go down, but some was reflected. There it is. The reflection, indeed, we will liken in a short time to an echo. Now, the sound business we are to deal with are compressional or longitudinal waves. Longitudinal waves. And the velocity of sound in air is given by the square root of P over D, where P is the pressure of the atmosphere and D the density. And I hope you see that that pressure business may be likened to an elastic factor and the density business to an inertia factor. Now, there are other kinds of waves, torsional waves. Let me illustrate what a torsion is. Here is a piece of chalk. I hold the upper end firmly, and I twist the lower end. Yes, and if one looked closely, the way this was sheared, this suggests very clearly that a torsional wave advanced along the rod. Yes, let's get that again. The camera got that very well. Yeah, notice how, where is it? You see it is sheared in a twisting way. Now, regarding the velocity of sound, an illustrative matter. Here I have an array of steel spheres on a track. They are highly elastic. I take one up the plane, allow it to collide with the system, and watch how quickly this one feels the impact of that one. Right away. Now we are to view that as the advance of a compressional wave, because that steel ball may be viewed as having a little spring inside which suffers some compression, and that compression runs away. Notice we have a little diversion. A compressor has suddenly gone on, but that's no hurt. You hear a sound, a compressional wave is reaching my ear and the microphone, so nothing to be worried about. What I wanted to say here is this. How fast does this compressional wave advance here? Well, the compressional wave that emerges from my mouth is traveling at about 1,000 feet per second. Here in steel, this compressional wave, 15,000 feet per second. So if this were a foot long, I'll make it a foot long. If that were a foot long, this one would feel that one in 1/15,000th of a second. So we have transverse waves where the particle disturbance is at right angles to the energy propagation, and a compressional or longitudinal wave where the particle disturbance is in the direction of the energy propagation. And we will see later that transverse waves can be polarized. Imagine that rubber tube whose end is fixed over there and I have the free end, and I do this to it. You know, a wave advances down the tube like this. Yes, down the tube. And if I had a picket fence with a slot like this or a slit, you can see that that wave could go through there. But if I had it turned like this, it could not get through. And thus we discover that transverse waves can be polarized, but longitudinal or compressional ones cannot. So sound cannot be polarized. But sound waves suffer all the other properties of waves. They can be reflected, that's why we get an echo. They can be refracted, that's why you can hear a band around the corner of a building. They can be absorbed, sure, if there were an audience out here, the clothes and the hair and the whatnot, the seats that are all plushed and fancy would absorb the energy. Now, water waves, another kind of a wave. Very troublesome thing, because water waves are a mess. But I want to show you a water wave and write some mathematics, because it is very enchanting. Here is a tank of water. I am going to drop a little body in this tank of water, and a little disturbance will result, which goes down the trough. Well, it isn't too large an amplitude, so I'm going to make a bigger one. Watch it. There is a wave. There is a wave. And I'm going to write for you the velocity with which water waves move. And for this purpose, I draw from my notes, because I have a secret to tell you. I do not ever bother to remember formulas. Indeed, I let my students take examinations with all the formulas from all the books in all the languages of the world written on them, because memory has not much virtue in my business. It is what we understand that counts. So I emphasize this. Knowing something is quite inadequate. What you must do is understand it. So here is the velocity with which a water wave moves. And notice how much troublesome. G lambda, where lambda is the wavelength, over 2 pi plus 2 pi t over lambda rho. Now somebody says, oh my God, Professor, that's gibberish. No. If the waves are very small, certain things apply. If the waves are very large, other things apply. This tells us the velocity of the propagation of water waves. Now, wave, pulses. Consider the following. Let there be an automobile engine here. Remember, imagination is a necessary ingredient. And I hear a knock in the engine. Something trouble. I want to locate it. What would I do? Well, I could take a rubber tube and put one end there and the other end to my ear, but that wouldn't reveal very much because wave conduction in a rubber tube is very bad. Let me put a metal rod. There's the trouble over there, I think. I put it there. Club, 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 club. I hear it very distinctly. Conduction along metal is very good, a compressional wave. And that is why, of course, this kind of an instrument works. A stethoscope. Oh, yes, I hear me quite clearly. I am alive. Yeah, that's a very, very important thing. Now, I have spoken of propagation of a compressional pulse in steel, propagation of a compressional pulse in a rod. Consider, sound being a compressional wave mechanism needs something to compress. And therefore, we would show that sound cannot be propagated in empty space. That's why people on the moon could not talk with each other. For this purpose, I could have a bell in a vessel, take out the air more and more and more with a pump, bloop, 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 pumping out the air, and I would hear the bell less and less distinctly, which means what? Compressional waves, longitudinal waves, need a medium for propagation. Transverse waves go best where there is nothing. And that's why we have radiation, say, from distant suns, stars, and the like. So I have made clear, I trust, the fundamental distinction between transverse waves and longitudinal waves about which this series now is engaged. Sound, longitudinal or compressional wave mechanism. And I shall see you again.